Hello again. Today's lesson is on scientific notation. Scientific notation is really handy when we're dealing with very large numbers or very small numbers. Numbers that are extremely large or extremely small tend to contain a lot of zeros in them as placeholders. Transcribing these numbers, copying them down to use in calculations, has a huge potential for error because people just tend to miscount the number of zeros that are in them. Scientific notation also takes up a lot less space. In the upcoming lessons, we're going to see a few other benefits of scientific notation. It's handy when we're dealing with metric prefixes for things like megawatts or picoamps. Also handy when we're talking about significant digits, which we'll deal with a little later also. For today, we just want to talk about how to write numbers in scientific notation and how to get them out of scientific notation back into what we might call standard form, the way you usually like to see a number. So grab your calculator and your guided student notes. Let's get ready to go. All right, let's see. We're going to start off dealing with positive numbers. Once we learn how to write positive numbers in scientific notation, writing negative numbers in scientific notation is no big deal at all. So here we go. If a positive number is written in scientific notation, it's the product of two factors, and that means that things are being multiplied. The first factor is called a coefficient. You've heard that word before. We've had coefficients on algebraic terms like 7x squared, and the coefficient was just the first number, the number out front, that was being multiplied by the other part. Nothing has changed here. The only thing is that with scientific notation, our coefficients are limited in how big they can be. A coefficient is a value greater than or equal to 1 and less than 10. In other words, we want numbers between 1 and 10. It's okay to use 1, but it's not okay to use 10. There's our coefficient. The coefficient gets multiplied by the second factor, and the second factor is a power of 10. So when you see a positive number written in scientific notation, you'll see it like this. We have the coefficient, multiplied by, and we actually use the multiplication symbol that looks like an X, some power of 10. In our last lesson, you learned how to write things like 2 million using a power of 10. And all of the examples that you did then involved one non-zero digit, and then we wrote it using a power of 10. And to tell you the truth, I sneakily tricked you just a little bit because what you came up with was an answer in scientific notation. So let's take a peek at what you did before. You said 2 million is, well, let's see, I think we did it like this, 2 million. But we wrote the million part out in words. And then we changed it a little bit so that the million looked like a million written as a number. So we have 2 times a million is indeed 2 million. And then the last thing we did was to take the million and write it as a power of 10. So we have 2 times 10 to the 6th power. And this is scientific notation. The 2 is the coefficient, and of course 10 to the 6th is a power of 10. So the only thing we have to do today is figure out what do we do if we have more than one non-zero digit. In this first example, we're going to do this in the longest way possible, just so that you can see where everything comes from. We have, instead of 2 million, we have 2,900,000. 2,900,000. 900,000 is exactly the same as 2 million plus 900,000. And certainly 2 million is, well, 2 million. I'm going to write that in words. But here I'm not going to write 900,000 as 900,000s. I want to think of this in terms of millions. It's not a million. 900,000 is a little bit less than a million. But it is 9/10 of a million. Because the 9 is only one decimal place to the right of the 2. If we just had a little bit more, we'd have 3 million, but we don't. What we have is 2.9 million. And of course, you've heard of numbers like this before, especially on television newscasts. It just tells you we're close to 3 million, but not quite there yet. So written in scientific notation, 2,900,000 is the same as 2.9 times 10 to some power, and you already know that the power of 10 that we use for a million is 10 to the 6th. All right, now, until we get used to converting numbers back and forth between scientific notation and standard form, it's not a bad idea to use your calculator and make sure that your end result matches the beginning value. 2.9 million is small enough for your calculator to display all of the digits, so let's try it here. We have 2.9 times 10 to the, which you can do as times 10 and use the caret key for a power, but if you want, you actually have a scientific notation key right here, and it's just waiting for you to fill in the 6. 2.9 times 10 to the 6th power is that much. And now see, you have to go up here and go 1, 2, 3, 4, 5 zeros, a 2 and a 9. 1, 2, 3, 4, 5 zeros, a 2 and a 9. It takes a little bit to double check, right? There's a lot of zeros there. We could have more zeros there. It's really hard to visually tell how large this number is. Scientific notation tells us exactly how many zeros we're going to have, because we have to go past the 9 and then add on 5 more zeros to get the 6 decimal places that the exponent shows us. All right, but that's pretty much it. So when we come here and we look on the next page, there are actually some steps for writing a number using scientific notation. This is probably a little more detail than what we need, but for right now, we'll follow them, and hopefully you'll get used to it pretty quickly and you won't even need to read this. But in general, the first thing we do is figure out the coefficient that we're going to use. Remember, it needs to be something between 1 and 10. After that, we figure out the digit that we're going to use for the exponent. That has to do with the number of places between where the decimal point was and where the decimal point is going to be. And then we figure out what sign we're going to have on the exponent. Remember, if we have something very, very small, close to 0, between 0 and 1, the exponent on the 10 is negative. If you have a large number, something bigger than 10, the exponent on the 10 is positive. And that's really all there is to it. So let's give this one a try. Here we go. Writing 417 million using scientific notation. So the first thing we need to do is figure out what's the coefficient. Where shall we put the decimal point when we rewrite this number? If I put it between the 1 and the 7, that's not going to work. 41.7 is too big. Remember, we have to be between 1 and 10. So we're going to slide it over here between the 4 and the 1. 4.17 is between 1 and 10. Now I need to rewrite this number because the type is just a little small for my electronic pen. There we go. All right. We're going to put the decimal point here, but the decimal point used to be over here. How far did we move it? 3, 6, that would be 8 spaces. So the number of spaces is 8. 8 is going to be the exponent on the 10. Is the exponent on the 10 going to be positive or negative? Well, it's going to be positive because 417 million is much farther away from 0 than 10. So we have 4.17 times 10 to the 8th power. I think your calculator can handle this one. Let's check. 4.17 times 10 to the 8th power. Yes. 1, 2, 3, 4, 5, 6 zeros, and then the 417. That's what we had before. If your answer is too large for your calculator to hold, like 5.2 times 10 to the 22nd power, your calculator is just going to look at you like you're nuts, and it's going to say, I'm not writing that. And it will tell you that's what it's worth, because it's just too long. So a lot of times, if you're dealing with very large quantities, your calculator will give you an answer in scientific notation. And the same is true for very, very small quantities. Anything that has so many digits that just won't fit on the calculator's display screen in one line. Okay, let's go on to the next example. We want to write 0.0175 using scientific notation. The first thing we need is the coefficient. Where shall we put the decimal point? Don't actually put the decimal point down. Use just a little marker that says I'm going to put it there. Because of course having a number with 2 decimal points in it doesn't make any sense at all, and people just tend to be sloppy about things and leave it where it doesn't belong. So the coefficient is going to be 1.75. The number of spaces between where the decimal point was and where the decimal point is going to be is 2. We moved past the 0 and past the 1. So the exponent is going to be a 2. Is the exponent going to be positive or negative? This one is going to be negative. And we know it's going to be negative because 0.0175 is really close to 0. It's between 0 and 1. So here we go. 0.0175 is equal to 1.75 times 10 raised to the negative 2 power. We're going to check this on our calculator just because we're getting used to the process, and we want to make sure the answer we wrote matches the value we started with. 1.75 times 10 to the negative 2 power. There we go. That's what we wanted, 0.0175. All right, let's flip the page. Wow, this one doesn't have very much space, does it? Hopefully that's a good sign for us. Our job is to write 3.58 using scientific notation. I know, it's not a really big or really small number, but that's okay, because if you're in a situation where you need to use scientific notation, it's convenient to use it for all of the numbers that you have at a particular time, not just the ones that are exceptionally long. So let's see. The first thing we need is a coefficient, some number between 0 and 1. And I think 3.58 is already between 0 and 1. So now we just need to multiply by some power of 10. All right, so this is not our answer, but let's just try some things here. When I do this in class, I usually ask for some suggestions. And the first one that I get is the smallest power that people think of as 1. And if you say 3.58 times 10 to the first power, that's worth 35.8. And that is not the value we started with. So that's too big. And then the second thing people suggest is 3.58 times 10 to the negative 1. And this is a good time to point out that we already know this isn't going to work. As soon as we have a negative exponent, we're expecting a number between 0 and 1, and 3.58 was never between 0 and 1 to begin with. 0.358 is not what we started with either. I'm not really quite sure what bothers people so much about having 0 as an exponent. But 0 is the answer that we need. Let's stick the 0 in here before I forget it. 3.58 times 10 to the 0 power. You might remember from our last lesson that 10 to the 0 power is 1. So saying 3.58 times 10 to the 0 power is like saying 3.58 times 1, which of course is just 3.58. All right, there we go. So now you know how to write any type of positive number in scientific notation. What happens if we have a negative number? And the answer is not a whole lot changes. Essentially, what we do is cover up the negative sign, pretend like the number is positive, rewrite it, and put the negative sign back in. This number line hopefully will prove to be a little bit useful for you. But the idea is this. If you have a small number that's close to 0, if it's positive or negative doesn't really matter, being less than 1 unit away from 0 in either direction will always give you the exponent on the 10 as negative when you write it in scientific notation. As soon as you get numbers that are more than 10 units away from 0, the exponent on the 10 becomes positive. And that doesn't change if the number is negative. The exponent on the 10 here is going to be positive also. The only thing that's different when you talk about negative numbers written in scientific notation is that you get a negative sign out front. But that's what you get with regular negative numbers as well. So it's no big deal. Let's try a couple of examples here. Our first one is to write negative 67,000 using scientific notation. Negative 67,000. Where do I want to put the decimal point? I think I'd like to put it right there. The decimal point used to be here. Where did it go? That would be, how many spaces? 1, 2, 3, 4 spaces. 4 spaces. All right. So negative 67,000 is going to be negative 6.7 times 10 to what power? Should this be a positive 4 or a negative 4? Well, if we were to pretend that negative wasn't there, I'll erase it for just a second, this would be really big. So we would expect the exponent to be positive. If we put the negative sign back in, nothing changes. Right, let's see. What color should I use here? Oh, geez. Let's just try black, I guess. This negative sign here is that negative sign there. Otherwise, it's exactly the same as if we had positive 67,000. And of course, we can try this out on our calculator. Negative 6.7 times 10 to the 4th power. There we are, negative 67,000. Really use your calculator to double check these until you're feeling extra good about converting. This next one is yours. Example 6, try on your own, pause the recording, come back when you're done. Is this the answer you got? I hope so. Let's talk about how I did that. Oh, I made a mistake, didn't I? Well, we'll fix this here in just a second. This exponent is wrong. So let's see what it should actually be. We have negative 0.00583. Oh, I see what the problem is. I've got 2 different numbers written on my page. Hang on. That should be better. At any rate, the first thing we did was to figure out where the decimal point is going to go. And we position it between the 5 and the 8 because 5.83 is between 1 and 10. And then we check and see how many spaces that we have. And we move that decimal point, gosh, I can't spell today, 3 spaces. This 3 needs to be negative. Negative because, slide this down a little, Where is 0.00583? It's in this yellow region over here. It's something very close to 0. This is a tiny number. The negative sign just sort of comes along for the ride. And let's use the calculator. We'll double check. Negative 5.83 times 10 to the negative third power. And there we have it. So the front negative has nothing to do with the exponent sign. Tiny numbers generate negative exponents. Negative numbers generate a negative out front. Sometimes you need one, sometimes you need both. Let's check the next page. All right, so now we're ready to go backwards. We'll go the other way. The number line is our key. Tiny numbers between 0 and 1 or between 0 and -1 have negative exponents. Numbers more than 10 units away from 0 have positive exponents. Doesn't matter if the number is positive or negative, the exponent on the 10 will be positive. All right, so let's check this one here. We would like to write 5.86 times 10 to the 6th power using standard form. What number is that? And the first thing we want to do is focus here on the exponent. This exponent is positive. I'm going to make it blue just so we pay attention to it. There we go. That means this should be a big number, more than 10 units away from 0. So we have a 5, we have an 8. The decimal point used to be here, but it's not going to be there anymore, so don't write it down. Just put a little mark there so we can keep track of where it was. In order to make this large, because we need to be far away from 0, we have to move 6 spaces. The 8 already takes up one of those spaces, so we're going to need some placeholders, and that means 5 zeros. 5.8 times 10 to the 6th is 5,800,000. Yes, 5,800,000. You actually should have expected that this number was up in the millions because we've used 10 to the 6th as an example several times now. And hopefully that starts to become familiar with you, that 10 to the 6th represents millions. Let's try example number 8. We would like to write negative 7.935 times 10 to the 2nd using standard form. All right. I'm going to pretend that this number is not negative and just talk about 7,935. I'm going to put my negative down here so I don't lose it. But the decimal point used to be between the 7 and the 9. This exponent is positive, which means I'm going to end up with a number that is far away from 0. It's got to be bigger than 10. It's not bigger than 10 at the moment. The only way to make it bigger than 10 is to move that decimal point to the right. And of course, 10 to the 2nd, that's 100. When you multiply things by 100, the decimal point moves a couple spaces to the right. All right, we're just counting spaces. So this should be negative 793.5. Again, let's double check. Negative 7.935 times 10 to the 2nd power is, there we go. Good, we make sure that what we started with matches our ending value. All right, this last one is yours. Pause the recording, take a few minutes, come back when you're done. Does your answer look like mine? Probably a little hard to tell. You have to stop and count all of those zeros, don't you? That's where the beauty of scientific notation comes in. Everybody should be able to convert 6.47 times 10 to the -9th without missing any of the zeros. All right, here we go. Let's double check it. We have 647. The decimal point started off right there, but it's not going to stay there. Times 10 to the 9th, I'll make it yellow so it matches with what we had on our number line, means that we have a very, very small number. In order to make 6.47 very small, we have to move the decimal point 9 spaces left. Now the 6 is already there. That takes up one of the spaces. So then I need 8 more zeros. 1, 2, 3, 4, 5, 6, 7, 8. We'll put the decimal point right here. And just so that we can find it, I'm going to put an extra 0 out front. So when you did yours, if you ended up with a decimal point, 8 zeros, and then a 647, you did it correctly. And that's pretty much all there is to it. On the next page, we have some application problems that involve scientific notation. And these are here not because they are new things for us to learn. These are here mostly because we don't want you to freak out when you see them. I know a lot of people do, and maybe you do, but you probably shouldn't. Let's take a peek and see what these have to say. We'll come back to this top stuff in a second. We have a series circuit with a total voltage of 6 times 10 to the 3 volts and a total amperage of 4 times 10 to the negative 3 amps. Our job is to find the total resistance. You already know how to find resistance. Do not let the presence of these numbers in scientific notation cause you to panic and forget what you already know. You know that you need to take the volts and divide by the amps. That's all there is to it. It just looks a little different. We have 6 times 10 to the 3rd divided by 4 times 10 to the negative 3rd. All right, so we need to do this on our calculator, and here's where the problem is going to come. Let's write this down in a line. We have 6 times 10 to the 3rd divided by 4 times 10 to the negative 3rd. All right, if we do this on our calculator, maybe you should just watch me because this is going to be wrong and I don't want you to do any wrong stuff. If I do this, 6 times 10 to the 3rd, come out of the exponent, divided by 4 times 10 to the negative 3rd power, come out of the exponent, and divide, I'm going to get 1.5. And this is wrong, completely and totally wrong. So the question is, where's the mistake? And you remember a long time ago, we talked about order of operations. We have a bunch of multiplications and divisions here. They all have the same priority, which means that we do them from left to right. So if we had 6 times 10 to the 3rd, we would get 6,000. And then if you divide by 4, we would get 1,500. And then if you multiply by 10 to the negative 3rd, that's where the 3.5 comes from. The problem is that we don't want to just divide by 4. This 4 is part of the denominator. The whole scientific number, the whole number written in scientific notation is the numerator, and this is all the denominator. And with fractions, we want to divide the entire numerator by the entire denominator. So let's come back up here to the top. We need to use parentheses to hold the number together because the number has 2 parts, and if we don't use parentheses, the parts are going to separate. So let's try this one more time. Parentheses, right above your 8 and 9 keys, we have 6 times 10 to the 3rd power. Yeah, you should come along with this one. This one's going to be right. Use your arrow key to come out of the exponent, close the parenthesis, divided by, new parenthesis, 4 times 10. I could have used my scientific notation key, couldn't I? To the negative 3rd. It all looks the same. And come out of the exponent and close the parentheses. There we go. This is, oh gosh, what is that? a 1, a 5, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. So the total resistance of this circuit, 1, 5, 1, 2, 3, 4, 5 zeros ohms. 1,500,000 ohms. You know, your calculator has a mode right up here next to the second button. If you want things to be given to you in scientific notation, even if it's just temporarily, you can come down and arrow over so that SCI is highlighted and press enter. And you'll notice right up here at the top, it now says SCI so that you know you're in scientific mode. And so now when I press enter, there we go. We get 1.5 times 10 to the 6th. And that may help you so that you don't have to count all of the zeros that are sitting on your calculator screen. 1.5 times 10 to the 6th ohms. Clearly different than the 3 halves that we had a second ago. So make sure you use parentheses to hold your numbers together. Sometimes the parentheses are redundant and don't affect the order of operations at all, and sometimes they are. Me personally, I don't like remembering when I have to have parentheses and when I don't have to have parentheses, so I just use them all the time to hold my numbers in scientific notation together. All right, let's try one more. There we go. We have a generator. If the generator were 100% efficient, it would produce 4.25 times 10 to the 8th watts of power. This is a big generator, like for a building, a big building. The generator happens to only be 85% efficient, so we want to know how much power does it produce. Again, don't let the presence of numbers that are written in scientific notation cause you to forget about everything else that you've learned so far. You already know that we can use a word equation to talk about this, that the output is 85% of the whole. The output is what we're looking for. Is turns into equals. 85% is 0.85. And the whole, 4.25 times 10 to the 8th. All right, and that's all there is to it. This one we didn't even have to do any algebraic manipulation. We just want to multiply. Okay, so here we go. 0.85. Notice that my calculator, whoops, is still in scientific mode. That doesn't mean you have to enter numbers in scientific notation. It just means it's going to give you answers in scientific notation. Times, parentheses to hold my number together, 4.25. I'm having trouble with this calculator, aren't I? 25, there we go, times 10 to the 8th power. Come out of the exponent, close the parentheses. There we go, 3.6125 times 10 to the 8th. 3.6125 times 10 to the 8th, and those are watts of power. Now, of course, if somebody wants to know how much that really is, we could convert it. It's not hard. We know that we need a 3, we need a 6, a 1, a 2, a 5, and the question is, where's this decimal point going to go? Times 10 to the 8th tells us that this is going to be a very large number. So we need to move to the right 8 spaces. From here over to there. 8 spaces. We already have 4 of them taken up by the 6125. So I better put in 4 more zeros. Units, of course, aren't going to change. And maybe you want some commas. Just like that. All right, and that's about it. So don't let numbers written in scientific notation cause you any undue stress. It's just a way to help keep you from having to count and recopy all of those dreaded zeros. Give your homework a try. Become really good with going back and forth between scientific notation and standard form, and we will see you at the next lesson. Have a really great day. Take care. Bye-bye.